which fuel has a higher CO2 emission per kilogram of fuel combusted? So per kilogram of methane, is that higher CO2 emission, or kilogram of hydrogen, kilogram of gasoline, coal, or propane? Well, you have to know what they all are. So CH4 is methane. Hydrogen, gasoline we model as octane, C8H18. Coal, I know it's not 100% by mass carbon, but the good coal is higher and higher percentage mass by carbon. Let's say it's 90-some-ish percent, close enough to 100%. So we'll just, I know that's not true, but we'll say that coal is 100% by mass carbon. And then propane, C3H8. You're going to combust it, right? You're going to have oxygen to combust. And what does it go to? How many CO2s do I get? One CO2. Well, how many H2Os do I get for the combustion of methane? 2. I get nothing on the carbon dioxide when I combust hydrogen, true? But I get 1 H2O. Now, you can come back and you can fix the oxygen if you like, but that's not the important thing. The important thing is how many CO2s are produced per fuel. And in this case, guess what? How much CO2 per hydrogen? 0. That's the lowest. You don't have any CO2 production when you combust hydrogen. Okay, so let's not worry about some balance for the oxygen, because that's really not the important part. But what about the gasoline? Does it go to 8 CO2s? And just to complete it, how many H2Os? 9. And for the carbon, how many CO2s? 1. And for the propane, 3 CO2s and 4 H2Os. Okay. So for each one of these, you can get the number of moles of CO2 produced. Let me put it as a column header. Number of moles of CO2 produced per number of mole of fuel. True? So what is it for methane? 1 CO2 produced per mole of fuel. What about the hydrogen? 0. What about the gasoline modeled as octane? You get 8 CO2s per mole of the fuel. How about for the just carbon? We're modeling coal as pure carbon. 1. And how about for the propane? So it looks like gasoline is really bad. It produces a lot of CO2. But look at the units. We want the per kilogram of the fuel. So why don't you do this? Why don't we calculate the mass of CO2? Often they report tons of CO2 emitted into the atmosphere, polluted into the atmosphere, right? Per ton of fuel, or whatever unit of fuel it is. So let's just do kilogram to kilogram. How do I move between the two? Is this equal to the number of moles of CO2 times the molar mass of CO2? The number of moles of fuel times the molar mass of the fuel? So really I take that ratio, which I just computed, multiplied by the molar mass of CO2, 12 plus 16 plus 16, 44. And then I have to look up the molar mass of each of the fuels. What's the molar mass of this CH4? 16. It's 12 for the carbon, 1 for each of the hydrogens. What is this one? 2. What is this one? 12 for each of the carbons and 1 for each of the hydrogens. And it comes in at what? 114 or thereabouts. How about the coal? 12. It's 12 for 1 carbon. And then propane, every carbon, there's 12, so multiply by 3, and then add 1 times 8, and you come in with right around 44. So you'll take and divide by 16. This comes in with about, what is this, 2.7, 2.8, 2.75 kilograms of CO2 per kilogram of that fuel. 0 for hydrogen, and then we'll have 8 times 44 divided by 114, and so gasoline comes in at about 3.1 or 3.08 kilograms of CO2 per kilogram of fuel. They all have the same units. How about the coal? 1 times 44 divided by 12, and it comes in at 3.7 or thereabouts. So that's how many kilograms of CO2 are produced when you burn 1 kilogram of coal. Well, I know it's not 100% carbon, but there you go. And then it'll be 3 times 44 divided by 44, about 3 kilograms of CO2 per kilogram of fuel. So which one? Which one has a higher CO2 emission per kilogram of the fuel? Coal. It's the dirty one. I know there's other things that make coal dirty. What are they? Sulfur and mercury. Sulfur and mercury. Those are the big health hazards. There's also particulates with the fly ash and other things, but sulfur and mercury. Now, once you solve that problem, you're ready to go to which fuel has a higher CO2 emission. Let's say how many kilograms of CO2 go out the stack per kilojoule of heat release. So that's M of CO2 divided by Q. And check out the units. It's going to have the units of kilograms of CO2 per kilojoule of heat release. Well, we just did the for each of these fuels, for CH4, for H2, for C8H18, for carbon, coal, and C3H8, we just computed the mass of CO2 per mass of fuel. And we reported it in kilograms of CO2 per kilograms of the fuel. And so for methane, it was around 2.75. Forget that one. For hydrogen, 3.08, 3.7 or 6.7, actually 6.7, and about 3.0. But I want a different number now. So how do I take this information and move it to the CO2 emission per kilojoule of heat release? Well, I'll take and have, this is what I want, right? I want the mass of CO2 per Q. This is what I have, the mass of CO2 per the mass of fuel. What do I need to multiply by? How about the mass of fuel to get rid of that? And Q. Wouldn't that do it? So what's the ratio of Q per M of fuel? Q, how much heat release per mass of fuel? What parameter have we studied and used throughout this, in the combustion chapter, last chapter? What was that known as? HV. What does HV stand for? Heating value. You could have the lower or the higher depending on how the water goes out. Just use the lower because it's really hard to get water to go out in the liquid state, in your flue. Okay? So we're going to use a lower heating value. Isn't that what that is? So you just take and divide. You look up, let me do this. Look up the lower heating value for each of these fuels. So for methane, it was something like 50,020. What are the units? Kilojoules of heat release per kilogram of that fuel. What about for hydrogen? I know I'm not going to do anything with it, but it's 119,950. There's a lot of heat release when you burn hydrogen, pure hydrogen. How about for the gasoline? 44,430. And for carbon, 32770. And for propane, 46,360. So you do the ratio, and so you're taking the 2.75 and divide it by 50,020, and you come in with the answer that we want. And I'm going to have to erase something here so it doesn't confuse everybody. But it's the mass of CO2 in the emission per heat released in the combustion of that fuel. And we find that it comes in at around 0.055 kilograms of CO2 emitted per 1,000 kilojoules of heat release in the combustion. How about for the hydrogen? Well, forget it. Just leave it off because it's 0. How about for the gasoline? 0.069 kilograms of CO2 per 1,000, kilojoules. And then for the coal, what does it come in at? 0.112 kilograms of CO2 per 1,000 kilojoules. And then 0.065 kilograms of CO2 per 1,000 kilojoules. So which one is the big polluter? Coal. Why do we remember Robert H. Goddard, who lived in these years, 1882 to 1945? Robert H. Goddard. This is because of his work in hydraulic turbines, because of his work with modern rockets, because of his work on the psychrometric chart, because of his work on the nuclear bomb, or because of his work on gas turbines. Rockets. The man is correct. And there's a NASA Space Center named after him. And why would NASA name a space center after him? Because NASA's very much interested in rockets to throw things out of the Earth's orbit. So it's a Goddard Space Center. Why do we remember Josiah Willard Gibbs, who lived from 1839 to 1903? I'll take the first volunteer to raise his hand. Was it because of thermodynamic relations, modern rockets, supersonic nozzles, temperature scales, or gas power? Thermodynamic relations, right? A, you're absolutely correct. What is a mini-split air conditioning system? Is it saying that it has a single evaporator and multiple condensing units? Does it have multiple evaporators and single condensing unit? Single evaporator and a single condensing unit? Is it a packaged air conditioning system often placed on roofs of buildings? Or is it commercial air conditioning system often placed inside of buildings? I want you to take a minute, raise your hand if you want to volunteer to supply the answer. I'll call on you after I see your hand raised. Did you say E? E? Thank you for participating. C? Thank you for participating. Multiple evaporators and a single condensing unit. Correct. Consider the hypothetical problem of 1 kilomole of CO2 that dissociates at 25 degrees C in 1 atm to form an ideal gas mixture of CO2, C2O4, and CO2 in which the amounts of C2O4 is given to be so many kilomoles. Determine the amount of C2O4 in equilibrium when you change the pressure from 1 to 2 atm and leave the temperature at 25 degrees C. Hypothetical problem. So you just have to say, oh, I have something that's dissociating. You look at this long and hard, and it dissociates into that. You have to use an analogy. You have to go and look, well, we studied some equations. We've studied like this. H2 goes to 2 H's. We studied N2 goes to 2 N's. We did 2 O's go to 2 O's, right? C2O4 2, are the carbons balanced in that? Are the oxygens balanced in that? It's the dissociation of this made-up C2O4 into two CO2s. Ready to study it now? So now they say you have case A, or case, whatever you want to label it. Let's call it the initial case A, because we're going to have problems with syntax. And initial case A says that I start with 1, the number of moles of C2O4 starting with in case A is equal to 1 kilomole. It's right here. I start with 1 kilomole of that. After I let it come to equilibrium, some of it dissociates. And so the amount of C2O4 in case A in equilibrium is equal to 0.6982 kilomoles. Does that make sense? Okay. So it's going to be tough, but you think about this. A lot of the book will introduce a notation like epsilon, the extent of the reaction. If I start with 1 and I come over here after the reaction, I have 1 minus the extent of reaction. All of that is for the C2O4. That all explains what happens to the C2O4. I start with nothing for the CO2. At the end, how many, in terms of epsilon, the extent of the reaction, how many CO2s do I have in the mix? 2 epsilon. Because if there was 0.1 that actually dissociated, how many I get? For every 1 mole of C2O4 that actually dissociates, I get 2 CO2s. Just like I get, for every H2, I get 2 H's. And for every O2, I get 2 O's. Okay, so what I can do is I can say that the number of moles of CO2 for case A is this 1 atm and 25 degrees C in equilibrium is going to be 2 epsilon. Well, I got to figure out what epsilon is for this problem, for case A. 1 minus epsilon is 0.6982, hence epsilon is 1 minus 0.6982, and then 2 times that is equal to, what is it? So hold it. Epsilon then is 0.3018, and 2 times that is 0.6036. This seems really weird because now, what is the total number of moles for case A in equilibrium? 1.3018. That seems weird. How come I started with 1 kilomole, now I've got 1.3 kilomoles? Doesn't this seem weird? Did we just violate conservation of mass? Nope, we didn't violate conservation of mass. It just dissociates. 1 big heavy molecule, some of them went into 2 smaller molecules. That's all. All right. Now that we got case A down, we got to go and shift to case B. Okay, so what's the difference in this one? This basically is 2 atms, where case A was 1 atm. The same temperature, right? So we want to know how many moles of C2O4 in case B are in equilibrium. I don't really know the extent of the reaction for case B. So what I'm going to do is I'm going to say it's just 1 minus the extent of the unknown reaction for case B. Make sense? And then how many moles of CO2 for case B are in equilibrium? That's going to be 2 times the extent of reaction for case B. And the number of moles total for case B in equilibrium, that's going to be the sum of that. It's just going to be 1 plus the extent of reaction for case B. So I really need to find the extent of the reaction for case B in order to then calculate the number of moles of CO2 and the number of moles of C2O4 in equilibrium. Well, what's my general equation K, function of temperature only, equal to, and then we look at our general equation right here, we model it to get we get the number of moles of CO2 to what power? Square it. Divided by the number of moles of C2O4 in equilibrium times the actual pressure divided by 1 atm. I'm going to run out of room. The number of moles total to what power? 2 minus 1 or 1. Thumbs up if you like that. Good. Now, how about this is all for case A. How about down here, case B? The same equation applies. So we have that case of T for case B is equal to the number of moles of CO2 for B in equilibrium squared, divided by the number of moles of C2O4 for case B in equilibrium times P2 divided by number total B all to the 1 power. I should have put a total. Sorry about that. This is the pressure at A, the number of moles of CO2 at A, the number of moles of C2O4 at A, the number of moles total at A. Well, are these K's the same? Because it's 25 degrees C, 25 degrees C. You didn't change K. So I'm going to write this equation down. Sorry, I have to scroll down. But we have the number of moles of CO2 case A in equilibrium squared divided by the number of moles C2O4 in equilibrium for the initial case A times 1 atm divided by 1 atm divided by the total number of moles for case A all to the 1 power is equal to, now instead of right here, I'm going to start substituting what we have. So the number of moles of CO2 for case B in equilibrium is 2 epsilon B squared divided by 1 minus epsilon B. The pressure at 2 is 1 divided by 1 atm divided by 1 plus the epsilon B all to the 1 power. So you have an equation. You can now solve for E sub B, epsilon B. When you solve for the epsilon B, you get that it's 0.2184. Meaning we can go back and fill in the blanks for at equilibrium from these equations right here. We'll have the number of moles of carbon dioxide for this new case at a higher pressure of 2 atm is going to be 0.437 kilomoles, and the number of moles of C2O4 is going to be 0.782 kilomoles. Methane at 298 1 atm enters the reactor operating at steady state and burns with not enough air, only 80% theoretical air. And the air comes in hot at 500 Kelvin. So that's another twist in when you do an energy balance. But the fuel does not come in hot. It's just methane at 298. Okay. An equilibrium mixture of CO2, CO, H2O, H2, and N2 at a very high temperature of 1500 Kelvin at 1 atm leaves. Determine the composition of the exiting mixture. So what we want to solve for is the number of moles of CO2 per mole of fuel, the number of moles of CO in equilibrium going out per mole of fuel. What's our fuel? CH4. And the number of moles of H2O gas going out, the number of moles of H2 going out, and the number of moles of N2 going out. All 5 of those are going out. But we're going to do it all per kilomole of fuel. All right. So what we do for the part A is we start and we get 100% theoretical air balanced equation burning methane. You've done it a number of times. CH4 plus O2 plus 3.76 N2 goes to CO2 with the 1 to balance the carbon, 2 H2Os to balance the hydrogens. Come back and put a 2 there to balance the oxygen, and we'll come out with 2 times 3.76 N2. Leave that one alone. Now modify it for 80% theoretical error. And leave the amount of fuel coming in the same. Well, you get 0.9 times 2 times O2 plus 3.76 N2. Isn't that? It's 0.8, sorry. It's 0.8, right? 0.8. 80%? Is that good now? Thank you for the correction. And now we're going to go, and we can leave it this way. We can say we don't know the number of moles of CO2 that go out when we burn 1 kilomole of the fuel. We don't know the number of moles of CO that go out when we burn 1 kilomole of the fuel. We don't know the number of kilomoles of H2O that go out when we burn 1 kilomole of fuel. We do not know the number of H2s that go out when we burn 1 kilomole of the fuel. And we don't, now we do know though, you can do this math, 0.8 times 2, that's going to be 1.6. And then you do the 1.6 times 3.76. We know that there's 6.016 moles of N2, or kilomoles of N2, per kilomole of CH4. So that one we know. So we can come up right here with 6.016 kilomoles. Right? But we need to now find these. I have my equilibrium reaction equation. For which reaction equation? Well, we go and look and we say, this is the reaction equation that works. CO2 plus H2 combining back and forth CO and H2O. And we can write down then that the equilibrium constant evaluated at 1500 Kelvin for this reaction equation must equal to the amount of CO in equilibrium, the amount of H2O in equilibrium, divided by the amount of CO2 in equilibrium and the amount of H2 in equilibrium. We could put the parenthesis with the pressure and over the sum total, but what you find is that exponent's 0. You've done it, right? So there's one equation that links them in. We need other equations, so we'll do a carbon balance equation. If you do a carbon balance equation and you introduce the concept that the unknown Z is the number of moles of CO. We've done a couple of these before. When you do the carbon balance, every time you see the number of moles of CO2, you can replace it by 1 minus Z. True? Then you do the oxygen balance. When you do the oxygen balance, you're left with the result that anytime you see the number of moles of H2O, you can replace it by 1.2 minus Z. And the next balance is the hydrogen balance. And anytime you see the number of moles of H2, you can replace it by 0.8 minus Z. If I knew you hadn't done those steps a number of times, I would go very slow. We reduce 4 unknowns and 4 equations to 1 equation with 1 unknown. And so you'll get that K is equal to Z times 1.2 minus Z divided by 1 minus Z times 0.8 minus Z. And we look up K, 2.56. And when we solve for Z, we find Z is equal to 0.3944. What does that mean? Well, that was the number of moles of CO in equilibrium. So 0.3944, I know, let's round it off, 0.394. In the next step, for part B, we'll keep all those digits. Then for the number of moles of CO2, you calculate 0.606, number of moles of H2O, You calculate 1.59, and the number of moles of H2, 0.406. All of these have kilomole, 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 kilomole. That's the answer to part A. Was very similar. Now the hard part, right? Energy balance. So let's read for part B. It says, what is the heat transfer from the surroundings to the reactor in kilojoules per kilomole of the fuel? Methane. I need another page because this one's full. So for part B, what we're asked to calculate is Q dot divided by N dot of the fuel. Make sense? Wasn't that the sum over all of the products? Some number of moles for 1 mole of fuel of each of those products times the molar enthalpy of the product minus the sum N H bar over all the reactants. So, and every one of these H bars is an enthalpy of formation plus a change in molar enthalpy from the reference state to whatever state it is. If it's for the products, the product exit temperature. If it's for the reactants right here, it's going to be the inlet reactant temperature. So plus delta H bar. Okay, so we have to do the sum. Now I'm going to do it for, we have a carbon dioxide in a product. We have carbon monoxide in a product. We have H2O in the products. We have H2 in the products. We have N2 in the products. Did I cover all the products? And then we have CH4 in the reactants. We have O2 in the reactants. And we have N2 in the reactants, right? Okay. So you have to put then the number of moles of the CO2 in the products. Didn't we just solve for that? I know I'm just kind of feeding you some numbers here so you can see that some of these you just calculated, 0.6056 for the CO2. And then you have to go, okay, I'm going to multiply by the enthalpy of formation on a molar basis for the CO2. We know that, can look it up. And here's the rub. You would normally say this is the molar enthalpy of CO2 evaluated at the exit temperature of 1500 Kelvin minus the molar enthalpy at 298. That's great. There's a couple other ways to do this. If you want a delta H bar, you can do C sub P bar times T exit or T out minus the reference temperature. T2 or whatever you want to know minus the reference temperature of 298. Right? So everybody didn't have a trouble except for H2 in the products. There's not a table like there's a table for CO2, CO, H2O vapor, and N2. This book doesn't give you that H2 table. Other thermodynamics textbooks do for this class that we've used in this, for this type of class, Thermo 1 or Thermo 2. So in that case, you would want to use the C sub P bar 1500 minus 298. Where would you get the molar specific heat for hydrogen? There's a polynomial expression for it, okay? And I also think that there's a table for temperature-dependent specific heats, and I think in there is a hydrogen as well, but it's on a mass basis. You're going to have to use the molar mass to go from the mass basis to the mole basis. Make sense? Now, look at the temperature. It's going from 300 Kelvin to 1500 Kelvin. Evaluate the specific heat at the average temperature of those two, and that's close enough. So you take 1500, add 300, 1800, divide it by 2. Evaluate this C sub P bar at 900 Kelvin good enough. Okay? Make sense? Can I just show you maybe the result on an Excel spreadsheet? And that way you could check it real fast. Let me see if I could pull it up. So this is the equilibrium amounts of the products, as well as their mole fractions. If you wanted to do mole fractions, it's right there. What I have to do is do an energy balance equation. So all of my N's are methane, oxygen, nitrogen. The molar mass, I tabulate. The amounts coming in kilomoles. The enthalpy of formation, C sub P bar, but I didn't even evaluate it for methane because it comes in at 298. So when you do this, I know I'm doing it H of F plus C sub P times delta T, but that delta T was 0. But how do we get this one? Well, you can do it a couple ways, but that is the molar specific heat for oxygen and the molar specific heat for nitrogen at an average temperature of about 400 Kelvin. And then down here, we do the same thing. You have carbon dioxide, carbon monoxide. You use those coefficients that came from the equilibrium equation. And then you have to get those specific heats. And you evaluate those specific heats at about 900 Kelvin. Do the sum over the products minus the sum over the reactants, and then Q dot over N dots around 260,700 kilojoules per kilomole of fuel.